Hi, in this video, we're going to look at how non-random mating can change the expected number of genotypes by doing a practice problem. But before we can do a practice problem, we're going to have to make sure that we're on the same page. So an important term to know is the fixation index, or capital F, and that is the probability that individuals will have the same alleles as a result of inheriting them from a common ancestor. And the fixation index has a value of ranges from -1 to +1. When F is negative, that means that disassortative non-random mating is occurring. And disassortative mating is when organisms mate with individuals that have a different phenotype. And that phenotype is a reflection of a genotype. So this increases the number of heterozygotes because individuals have different genotypes. So for example, big B is mating with little b, and as a result, those two different alleles are brought together in the offspring to make heterozygotes. When F is 0, that means random mating is occurring, and when F is positive, a positive value, that means assortative mating is occurring, and that's when individuals mate with other individuals that have the same phenotype, and that increases the number of heterozygotes because the parents have the same genotype, so their offspring will have the same genotype. And one thing I want to emphasize is that the sign of F determines the number of heterozygotes that increase or decrease. So on an exam, make sure to read carefully. So our practice problem. You're studying the inheritance of bending styles in the capital of the Earth Kingdom, Ba Sing Se. In a small school, you observe 48 earth benders, which is big B, 32 water benders, big B, and 20 non-benders, little b. So determine how the number of heterozygotes will change if there's non-random mating occurring in this population. So in order to see a difference between before and after, between non-random mating and random mating, we're going to have to calculate the number of expected heterozygotes in a population under Hardy-Weinberg. So to do that, the first thing we have to do is find the frequency of alleles. So to find the frequency of big B, we're going to do 2 times 48 plus 32 divided by 100 times 2. We're multiplying 48 by 2 because each waterbender has 2 alleles, and plus 32 because the heterozygotes only have 1 big B allele. And we're dividing by 200 because the population is comprised of 100 people, each with 2 alleles. And this gives us the frequency of 0.64 for big B. And for little b, the calculation is similar with 2 times 20 plus 32 divided by 200. And it's 2 times 20 because each non-bender has 2 alleles, plus 32 because each waterbender has 1 little b allele divided by the total of 200 alleles to give us 0.36 for the frequency of little b. And then to find the expected number of heterozygotes in this population, it's going to be the total number of people in this population times 2pq. And that gives us an expected number of 46.08 heterozygotes in this population. So when F is negative 0.36, how does the number of heterozygotes change? So one thing to notice is that the equation used to find the frequency of heterozygotes is changed. It's now 2pq minus 2fpq. And it's minus 2f because the number of heterozygotes is being impacted by both the dominant homozygotes and the recessive homozygotes. So in this problem, F is negative 0.36. So we're going to plug and chug all these numbers into the equation that we were given. So the frequency of alleles for the big B allele was 0.64 and the little allele Q was 0.36. And this should give us a frequency of heterozygotes as 0.626688. And to find the new number of expected heterozygotes, we're going to do the population number, which is 100 times that frequency, and that gives us 62.67, and that's an increase in the number of heterozygotes. And that makes sense because, as we said earlier, a negative number shows that this assortative mating is occurring, so we would expect to see an increase in the number of heterozygotes. And then for our second problem, this time F is positive 0.36. So when we plug that into our equation, that gives us the frequency of the heterozygotes to be 0.294912. And we're going to multiply that by the total number of people in the population, which is 100, and that gives us a new number of 29.49 heterozygotes expected in this population, which is a decrease. And that makes sense because F is positive, so that means assortative mating is occurring, and we would expect to see a decrease in the number of heterozygotes.